regard to energy, water, and environment systems, providing us an interdisciplinary exploration and focusing on the cross-relation among these different domains. Well, Professor Wang is a worldwide leading researcher in energy efficiency and energy conversion and chair professor at Shanghai Jiao Tong University, where he is also director of the Institute of Refrigeration and Cryogenics. He is certainly known even to the youngest of you also for being the current energy-in-chief of Energy, the international journal, and he has received a lot of recognition for his research activities, mainly established in the fields of heat pumps, green building energy systems, and energy water-air nexus. Author of more than 700 papers with over 40,000 citations, he has indeed received 3 national research awards and prestigious academic international awards, such as the Gustav Lorentzen Medal from the International Institute of Refrigeration and the Rittinger International Heat Pump Award from the International Energy Agency. In 2023, he was also awarded as a Global Energy Prize laureate in the New Ways of Energy application category. Then, Professor Wang, we can't any longer wait to benefit from your lecture titled Energy, Water, Air, Food, a Nexus Approach. So I would like to invite you to reach the stage, and the floor is yours. Thanks.
So good morning, ladies and gentlemen. It's really my great honor, and I was invited by Never and also Henrik to have this lecture. And because it's my third time to come to this conference, and it's a really honor for the 10th Jubilee annual meeting for this conference. So my topic is actually for energy, water, air, and food, a nexus approach. So it's a big picture if we talk about energy, water, air, and food, because for the United Nations, for the sustainable goals, it's related all to this. So, but for this research, it's a multidisciplinary research. In this case, 7 years ago, I established a small team, so-called innovative team on energy, water, and air. So this, I would like to say, in the last 7 years, what we have done, and to share our experiences. So why Itawa, this team was founded? So I started for this. Actually, this was the origin from publication, from science, from MIT, Professor Emily Wang, and also Professor Omayage. And maybe Omayage, maybe next 2 days, we will see whether he will succeed with the Nobel Prize for chemistry. Yeah? He's a good candidate because he's the father for morph materials and cough materials. Because they invented the technology in very dry regions with relative humidity 20 to 25%, with morph 801 could capture water and then generated with solar to release to get water for drinking. So this actually created a very, very strong point that a lot of people, they take attentions how to do some research work for atmospheric water harvesters. So actually, for this kind of researches, for our research group, we had a long term for this kind of studies. And also, just to start from 2002, we started this kind of research. At that time, we have publication in China. But then later, the student, so one student, Jiaying Wang, she is here, now she is an associate professor. So when she was a PhD student, she did the research work. And when the science paper was published at that time, in our laboratory, we have built the machine to get atmospheric water harvesting every day for 50 liters. So then, this makes our group to think, why 1 gram of water from morph materials, from very dry area that you get the publication in science, but we take 50 liters of water, we can only publish in applied thermal engineering or energy. So in this case, we made some considerations. And also, some years ago, we had some research work for the air conditioning, whether it's possible to get latent heat and sensible heat separated. And we created some technology to use desiccant materials coated on the heat exchangers, and we're using desiccant absorber moisture for dehumidification. In this case, for air conditioning, electric driven is used for cooling, but dehumidification was done by the desiccant materials. But for the desiccant material, you need to consider for the regeneration. We're just using the condensing heat for regeneration. So in this case, we could get a normal COP value for air conditioning to get 100% increased. So this has a great impact. But at that time, it's in the beginning that we try to seek the possibility to publish in high-impact journals. But at that time, had no experience. We submitted to Nature, and then transferred to Nature Communication, and then at last, finally, scientific reports. So my student told me, Professor Wang, scientific reports is also a part of Nature. So in this case, at last, I finally accepted we submitted, and also go through the peer review process, and at last, we pay $3,000 for the payment. This is an open access journal. So this is actually a very good publication, but unfortunately, we had very good results, but finally, is not in high-ranking journals. But we had another attempt. So because due to this experience, so when a cell-based journal, so-called JOR, was launched, and the second year, in this case, because the impact of atmospheric water harvesting in the world, then I contacted with editor-in-chief of this journal, Phillips Ellis, and whether they are interested to, if we contribute a review article. So then my proposal was accepted by them, and then we prepared, so the 3 students work with me, we prepared for the review paper for JOR. So it was published in August 2018. So this was the first time for me that I think now we have already contact with a high-impact journal. But at that time, the impact factor not yet ready. But I think this is a good journal. So in this case, this helps us have this kind of research and also encouraged our students. So this is why that I wanted to found a so-called innovative team on energy, water, and air. So because our team is working with solar energy, working with air conditioning and heat pumps, and also desalination. So energy, water, air are main criteria of my research group. So in this case, we consider also supported by the National Natural Science Foundation of China. So we encourage the researchers from 0 to 1. And actually, for my research group, we have long-term publications for 1 to 100. That's a LEA engineering program. For my group, even we published nearly about 100 papers in energy, actually. So in this case, we consider whether we could do something from 0 to 1. That means this is originated from this research that we could publish high-impact journals. So at that time, I set the goal every year, the small group, we need to publish 3 to 5 high-impact journals, minima Nature Communications, and even more higher journals. So then we start the exploration, try to explore in ground-breaking basic research from 0 to 1. So the first success is for the research and publishing in 2019, also in JOR. It's our completion, the first research papers. Really, we did for 2 years. And the student, actually, we, at that time, a lot of considerations for solid refrigeration, solid state refrigeration. Actually, we're using thermoelectric semiconductor cooling. But also, we are doing with the humidity. In this case, we coated the heat exchangers of the thermoelectric cooler, the both side, coated with MOF materials. And for the colder side, when we take it from low humidity, we could uptake moisture. And then moisture absorbed by the cold side, and then we switch into the hot side. just switch direction of the AC, from electrical current flow. So in this case, you get the regeneration. So in this case, we just make this switch. We could easily take moisture, very low humidity, to a high humidity. So in this case, it's a kind of concept, humidity pump. So in this case, we combine the concept of solid refrigeration with humidity pump, and then at last it was published in JAWS. So meanwhile, we had a secondary research paper, because at that time, for SARE, they launched another new journal called iScience. So we published another one for the solar-generated dehumidification. Actually, we took humidity from inside the door and take it into the outside in the absorption panel. But outside, we have a selective coating to absorb solar energy and to release humidity. So in this case, it's a kind of concept of humidity pump. So based upon these researches, because if we succeeded, one student succeeded, other students will be very, very active, try to do their best. So in this case, I think we had a lot of engineering work. 1 to 100, normally there's a big system, but for 0 to 1, usually a small system. It's a concept, mostly related research with materials. So in this case, we created some rooms and also have a plate, and I put some target journals for the students. I ask that whether in the next several years, we just fill the blank to see what kind of publication we could contribute. And meanwhile, so there is also a very important conference. This is ASME International Conference of Micro Nanoscale Heat and Mass Transfer Conference. So the conference organizer invited me several times to deliver a keynote lecture for the conference. But originally, I never participated in such kind of conference because I think I'm not doing nano scale. I'm doing the scale-up system. But after half a year, they contacted me again. They said, Professor Wang, you are doing adsorption refrigeration. You are using adsorbents. Adsorbents should be nanoscale. Why not? If we need somebody to say this, who will be most suitable? So finally, I think if you want me to say something of adsorption refrigeration, it's my research area. So in this case, I agreed, but for the conference, the topical, I set it as an adsorbent relative to energy, water, and air. So the reason is that at that time, already we started the research work, at least 2 papers published in JAWS, and other papers on the way under review. So in this case, I think it's good that the opportunity to communicate our research results with the international experts. And also, this is for the desalination. So Professor Xu Zheng, at that time, the young faculty member, so he is also today here. So we developed a lot of research work with solid desalination. And also, finally, so we started from 2018, and finally, 2019, after 1 year, so everything finished, and we sent our facility to MIT. So because we have some collaboration to be testified in MIT. So this helps us that this research is more well respected because it's from MIT. So in this case, we collaborate with MIT, and also finally we got good publications in energy and environmental science. So meanwhile, we tried some researches for the breakthrough in advanced materials. So we did some research work for the PCM materials for thermal storage. So in this case, thermal conductivity is very critical. So there are a lot of researches for enhancement of thermal conductivity of PCM materials, such as nanofibers and so on. But for us, if we consider we need to build the scale-up systems, we must use engineering materials. And in this case, we tried expanded graphite. Because expanded graphite, you could try to make it into like a plate and also scale up. And in this case, we could integrate this with PCM materials. And then also into a fixed form. In this case, we could increase the thermal conductivity for nearly about 70 times to compare with PCM. And finally, so this paper was published in Advanced Materials. But in this case, we collaborate. Also, the second last author, he is a very famous professor in Shanghai Jiaotong from a school of materials. So in this case, he instructed a lot for us how to get a publication in material science. So this actually is a very good story. So in this case, we succeeded with Joel and with advanced materials. So this makes that the whole group, especially the young students, inspired. And the inspiration is very, very important. And when this happened, I see before 8 o'clock, when I arrived at my laboratory, there are students doing experiment. So this, I think, just make the whole research group very, very inspired and active. And then, in the spring of 2020, we had publications, another publication in JOR, and energy storage materials, February, energy environment science, and Anger chemie, and then March, energy storage materials, and ACS material later. So this is actually several papers of the student. And at that time, Shanghai Jiaotong University, actually the homepage, at that time, there are 5 papers, but 4 papers are from our research group. And due to the COVID-19, so scientists nearly isolated, but at that time in China, we are free to move. But in the United States, actually, it's not possible for the scientists to come to the laboratory. But MIT, in this case, they organized international curricula on thermal innovations. This is suggested by Professor Gang Chen and also Professor Ruzhu Wang at MIT, at the department head of mechanical engineering. And then Professor Ruzhu Wang called me, and she's told me that we need to have this specific topic for water harvesting. So Professor Wang, who should be the lead candidate to organize this kind of workshop? So in this case, I will suggest this group, and then we broadcast online for this kind of just a seminar. So this is actually the seminar, and the MIT make the promotion for all speakers. So this is very important because I was promoted by MIT, and also to be honored, very honorable to be invited by MIT to do this online. And this is actually the topic for extracting water from air, energy, water, air nexus. This is the time, my talk in July. So then, after several years, this is to the end of 2024, all these are publication, because originally we cannot imagine, because my target is every year 3 to 5 high-impact journals. Now we had publications in Nature Living Materials, Nature Water, and JOR, and Energy Environment Science, and Nature Communication, Advanced Materials, so on. So this makes the whole group. We have 4 faculty members and nearly about 20 students involved. So in this case, this helped a lot of new achievement and also inspired the whole research group. Now I say something, what we have done for 0 to 1 and 1 to 100. So our research focus for Itawa team, normally we have atmospheric water harvesting and thermal management for electronics, and also dehumidification, humidity control, and energy storage, and also greenhouse for the plants, and also heat pump and energy storage, and then desalinations. So I just say some examples. The first is for atmospheric water harvesting. So this just shows, for the start point, we had publications in applied thermal engineering, and then again, applied thermal engineering, and then energy. So we have several steps, start from the materials, ACF, graphite, and silicon gel. And in 2015, we got 0.3 kilogram water for 1 day with solar. And then 2016, 14.5 kilogram water per day, and 2017, that's 50 liters. So because we got the project to develop a unit more than 30 liters water per day driven by solar energy. So this is the steps that what we have gone. But for the final steps, I asked Jane, and we tried to go through the high-impact journals. And in this case, we had a submission to Science, Nature, Nature Communication, Journal. So mostly sent to review, but finally rejected. The reason is that the concept of the final form is similar like that before, because there are no changes, but performance much better. So in this case, at the last we published in Energy because the student needed to finish her PhD. But also, we did some research work with morph materials. So based upon the experience from MIT and UC Berkeley, and all research group, we are experienced. Because even for the morph materials, for absorbed water, it has a limited adsorption because it's a physical adsorption. We did also a lot of with chemical adsorption. So in this case, we're using lithium chloride and try to get lithium chloride water impregnated into the micropores of the morph materials. So in this case, what we could see that is this work for the adsorption with the moisture. So it's to compare with the regular ones, it's much improved. And also based upon this, we did the work, get a passive solar-driven atmospheric water harvesting. And finally, this paper was published in Anglo Chemie International Edition. And also, we tried to use solar energy using solar collector directly, and we integrate solar panels, and in the backside with a condenser. So during the night, we open the adsorption, and during the day, seal it, and close it. And then solar radiation hit it, and we could get liquid water that's condensed from the condenser. So in this case, 1 square meter, you could nearly get about 800 grams of water. So, and also the size is very, very compact. And then later, we think it could be possible that to use solar energy, continuously operation, if the daily. In this case, we need the adsorbent with a high-speed adsorption and high-speed regeneration. So in this case, we're using lithium chloride onto this nano-composite adsorbent. And we're using specific technique to improve heat and mass transfer. So in this case, at last, we established solar-driven rapid cycling AWH devices. So in this case, for one day, we could operate maybe 8 cycles. So in this case, one day we could make good uses of solar energy efficiently. So this just shows 1 square meter per day, we could get about 2.3 liters of water. Also, we tested another results to the same early region in the desert area. And what we have done is that that area usually adsorption is very, very slowly, but we put adsorption materials in the night to absorb moisture from the air during the day for the regeneration. But we need a very short time for regeneration. So in this case, I suggest we get, maybe this is 8 units of this kind of adsorbent. So then during the day, each unit, so then we could generate 8 times. So in this case, we could get the more high yield of AWH. So this paper was published in Nature Communication. Later, I had visits, and from company, they wanted to make it a commercialization. And later, I will show you. So now we have a commercialization for atmospheric water harvesting. Also, the student, they learned how to do this kind of, just like in the theater, just somebody, they have a specific technology. So that means using morph materials, whether it's possible that we make a rotation that every day, 3 plates, and make it continuously adsorption, desorption. So this got actually 1 day per kilogram of to get about 2.11 liters of water. And also we are working with interconnected porous gel for high efficiency continuous. That's a solar atmospheric water harvesting. Actually, this is a specific machine, and we take hydrogen, just rotate. So when it's outside, so you get That's adsorption. But when it comes to the concentrated solar, you get a regeneration. And in this case, get a moisture water condensed. So in this case, what we have done to get 1 day per square meter, nearly about 15 liters of water. So this is a very, very big increase to make that this kind of technology could be market available or market interested. The second topic for the research is for electronic thermal control. And some years ago, that before I do not consider that we are doing this, but with this kind of morph materials, I considered that for the mobile phone, for example, so we using the near standard mobile phone for the testing, and when the electronic working load is lower, if it's coated with morph material, it could absorb moisture. But when the load goes higher, the temperature goes higher, so the absorbed moisture will be released. In this case, you will reduce the temperature. So this is a kind of, we call it sweet cooling, because it's similar like a human body for the sweet cooling. But for these cases, we demonstrate for the mobile phone, normally the maximum temperature could drop nearly about 8.6 degrees centigrade. So this verifies that it's very efficient, because for the materials of adsorbent with moisture, normally this is desorption heat is nearly about 2,000 joule per gram. To compare with PCM, nearly about 7 to 10 times increase. So in this case, you're just using about 1 gram, you will get such kind of electronics, the temperature, the well controlled. And also, students also practice with the battery thermal management, and just coated with morph material, and try to do the test and find that in this case we could also control the battery temperature below 45 degrees and realize self-preheating with increasing the battery capacity of 9.2%. So in the summer, cooling down, but in the winter, heating up by adsorption. So cooling down by desorption. So we tested such kind of batteries, and it's demonstrated here to be, try to keep it always working in a safe region of the temperature. And based upon this, we also tried, because my research group had a very good collaboration with Huawei for 5G station actually. And in this case, originally we had optimized our 5G stations, and because from 4G to 5G, Huawei wanted to keep the size unchanged. In this case, asked us to make optimization of heat exchanger. So it was successful. So nearly about 10 million units. Over the 10 million units, they used our structure. So we had a very good partnership with Huawei. So in this case, I am considering whether for 6G, how to use. In this case, I suggested to using this kind of sweeting cooling coated on the heat exchangers. What we have found for the 5G station we tested, we could get nearly about 20 degrees maximum temperature reduction with nearly cooling power, 600 watt per square meter. So in this case, this could be a very important issue. So finally, we had a passive thermal management of electronic devices. This is just a review article, so published in Device. We try to introduce how this could function. And so we try to consider its use for mobile phones, 5G stations, and any kind of batteries and so on, for the, even for the battery of charging and so on. And very recently, so my students think we could also do the PV cooling, because of photovoltaics in China, so we have a huge photovoltaic power station, but especially in the desert area, after use for a long time, there are a lot of dusts, but usually no water there. So they have a requirement to use water for the cleaning. So in this case, we tried that possibility to use a sweet cooling to cool down the PV photovoltaics. In this case, you could increase the energy efficiency to generate electricity. But meanwhile, we could produce water. So this is a concept for this research. So it's in the example to use future energy So this is published in JAW. And now we are doing the real one, and also cooling down of photovoltaics, but also meanwhile produce water. So the third topic is dehumidification and humidity control. So we start from this Joe. At that time, he was a student doing PhD work for 5G mobile phone cooling for Huawei. But this is not related to his PhD work, but he interested to this. And very fortunately, he got the first research publication in JAW. And then another student, actually his wife, they are classmates and working together. She becomes his wife. And she's doing for the nano energy. We published one paper for exergy efficient boundary and design guidelines for atmospheric water harvesting. And so in this case, we clarified to gate AWH. So in the climate regions, what's the boundary conditions? And also, 23, this is a postdoctor from that's a Primož Petruš. I think some of you may know his father, Petruš. That's from Slovenia Energy Association chairman, actually. So he became my postdoctor. And so when he was a postdoctor with me, he contributed one paper in science, one paper in JAW, and also one paper in energy environment science. So this just the idea, so-called sustainable cooling with water generation. But the editor would like the idea, if it's possible, to have these dual uses in the dry areas. So we just proposed a good idea how to reach dry area for cooling and also atmospheric water harvesting. And also another student we did using a thermoelectric cooling coated with Morph materials. Originally, we did for the humidity pump now, but this is also used for the atmospheric water harvesting to try to make it a very compact unit to get water harvesting. So 1 kilogram of material to get about 2.5 liters in this case per day. So next is for the energy storage. So this was the first example for energy storage in publication in advanced materials. This is the enhancement of thermal conductivity. But with this kind of enhancement, we tried to build this. This heat exchange without fins, we're using expanded graphite as a fin because the thermal conductivity is very high. So in this case, it's very easy, and we could create 1 kilowatt system, 1 kilowatt hour system, and then this is a 15 kilowatt hour systems. We just connect it. So it's very easy to be integrated, and we demonstrate. And also by adsorption researches. So adsorption of moisture, it will generate adsorption heat. So in this case, air temperature will be increased. So in this case, we consider whether we could use this as a thermal battery. But usually for thermal battery, what we found there is so-called a reaction wave, and we developed this model. Because the most important thing for this, how to get stabilize temperature output. Because if we have inlet temperature 20 degrees, heated to about 38 or 40 degrees, this is good for room heating. So in this case, we need the control of output temperature and also the control of the output power. So we developed the model and demonstrated and succeeded, and also had 240 kilowatt hour in 1 cubic meter. So this is a very high energy density for the adsorption thermal storage. And then I asked another student whether we could use this kind of technology for the thermal wall, actually for the solar. Because thermal wall normally used during the day for the room heating, but how to use it in the night. So in this case, we consider to put the honeycomb adsorption thermal battery into the wall. During the day, you get the regeneration of moisture. And heated also coming into the room, but during the night, so we could get some humidity come to the channel and then absorb it, and then heated air comes into the door. So in this case, we could demonstrate for the all the day usage, 24 hours, with effective heat delivery from low carbon building heating and energy consumption reduction could be nearly about 54%. So we demonstrated the normal thermal wall and also adsorption thermal battery wall, and we tested. So I think when the student is doing the research, try to find a very good topic. So this just based upon my swimming. During my swimming time, I think I got one idea. When I finished, I immediately come to student. This is your PhD work. I think could be a good idea. Then I ask this student to do, and she succeeded for this research. And also another work we're using atmospheric water harvesting with energy storage. So in this case, we used some hydrogen, and the hydrogen could get more high water adsorption. And so now this student also did a very, very successful job. And based upon this, because in the last years, there are a lot of interest for the radiative cooling. And during this process, I think 2018, I applied one project from the Shanghai municipal government for the greenhouse because they need greenhouse technologies. So in this case, we just using a solar radiation film for the cooling. In this case, to get nearly, this is the excellent cooling effect, nearly about 18 degrees centigrade reduction for the greenhouse to compare with normal greenhouse. So in this case, we are sure that we could use this greenhouse even in summertime with temperature 35 degrees. So we still could use the greenhouse inside to produce plants. So also the vegetables, what you got to compare experiment with the controlled ones, original ones, we have increased the quantity and quality. And also we tried another radiative film and use it as a cooling marker on the ground surface. Because in this case, we try to reduce radiation cooling for the reflection to the other side sky, and in this case, to get the root of the vegetables, to get a temperature nearly about 10 degrees down to compare with regular one. So even the room temperature is high, but the root is comfortable. So this is another thing what we could have done. And this you see with RC, that's an example. Others, there are three kind of other films we tested, but with a radiative cooling film as a cooling marker, it's really successful. We tested. Also, get Chinese cabbage yield, nearly about 127% increased. And this paper was published in Nexus, and because I tried with a JOR, and also Nature Sustainability, the both Senate review and the major revision, and then another review process, but the original review do not want to review again, then they invited new review. New review say rejected, then rejected. So at first, Nature Sustainability. And then to submit it to JOR, we got the same results. So in this case, it cost a long time, and the student wanted to get a graduation. And the Nexus is an open access journal, and also SDEWES. So Professor Jerry Yan is just the chief editor for this. So in this case, we published the first research paper in Nexus. And also now it's less than 2 years, but we could get, now it's about 30 citations because this is a very good research work. And also for the greenhouses, we demonstrated that even in Singapore, that my students come there in the rooftop because the humidity is high to uptake water from air and use this water for the greenhouse for the growth of plants. So in this case, we created 1 square meter. This area we did a test about 2 weeks, and we produced 1 square meter, nearly about 880 grams of water, and produced 1.28 kilogram of vegetable, actually. So this just shows the example, and another example we published in Nature Water by another student, and we use this kind of high hygroscopic gel for passive plant transpiration and soil evaporation water cycling. So this just got that water saving for greenhouses. We could get the saving nearly about 45%. So then we had some research with heat pump. This is our conventional area. Because other students published, and then heat pump students, they said, Professor Wang, we also need high impact publication. But I said normally it's not possible because heat pump is a very, very mature area. But we tried our best. The first that we developed water vapor high temperature heat pump and utilizing industrial waste heat. And we found water is good substances for the heating temperature output over 100 degrees centigrade. So that's a natural refrigerant, and so also efficiency is high. So we build a system for waste heat recovery from 80 degrees to 120, 130 degrees. So if you upgrade nearly 50 degrees, you get a COP value of 3.5. For 40 degrees, it's about 4.5. So we demonstrated this and also succeeded. And this was published in the 25th International Congress of Refrigeration in Montreal. And big competition. So finally, my student, Woody, in the middle, he got the first place for the student competition. So there are 3 students to receive the award. And another example is the 26th International Congress of Refrigeration in the year 2023 in Paris. Another student, and in collaborating with my engineering PhD student. So they're working for high efficient desiccant coated heat exchanger based heat pump to decarbonize the layer transportation. So this is based upon my solid desiccant dehumidification system to get a COP value 100% increased. And then we succeeded, demonstrate, and now this year it will start for the Lear application in the Metron's line in Shanghai. And also this student is very happy to receive also the first place, the best student thesis for the 26th International Congress of Refrigeration in Paris. So then this student, we collaborate with NTNU, Norwegian University of Science and Technology. So he feel a strong desire to get a publication in high impact journals. So we tried a lot of times. At last we had a research for heat pumps as a sustainable bridge for global heating and cooling at a multi-scale, because we consider something not in a small scale, but at the world scale, and to consider heat pump contributing for decarbonization, not only for heating, but also for cooling. So in this case, this kind of topic could be very interesting for big journals. And then we had another work for heat pump integrated with latent heat energy storage. Now we developed the whole models, and it's sponsored by a big project from a National Natural Science Foundation of China. We try to integrate heat pump with thermal storage. So in this case, we could take industrial heat or heat from the ambient air by heat pump and then get it stored into the latent heat. So you get nearly 3 times or 4 times increased. And then with this, we could use another heat pump, even increase to the industrial heating demand needed, or cascaded heating for the normal uses. So in this case, we got very, very flexibility for the uses of PCM materials. We select high density, safe, and cheap materials, maybe 60 degrees centigrade, for example. So then it will be easy for the market to accept. And also we had some tests for the intermediate thermal storage, because some areas, summer heating, winter cooling needed. So if we consider thermal storage, you need to consider heat storage and also cooling storage, cold storage in summer. But in this case, you need to double 2 tanks. So finally, we consider to have an intermediate thermal storage at about 15 degrees to 20 degrees. But we use heat pump, in this case, combined together to solve the need during the winter heating and summer cooling. So in this case, all the year operation, we could get more high efficient. And also, we tried this to consider with integration with the direct air capture. And the direct air capture, because they are also considered with the adsorber and the desorber, but adsorption process, you need the cooling, desorption process, you need the heating. So originally, it's a separate system. Now, we propose to use heat pump. And this heat pump, so the Professor Tiansu Ge, she's here. So she was responsible for this. This is a demo for nearly about 600 tons per year CO2, direct air capture from the air. So this is actually the first demonstration that we could see. We have the technology for negative CO2. In this case, now I think next year we will have more bigger systems for the demonstration. So finally, I say something about solar-based desalination. So just the first figure is a collaboration that we had, the first publication in EES, actually in collaboration with MIT, and also it was selected as top MIT research scholars 2020. So we using thermal localized multi-stage solar stir, and what we generated, solar GOR, so nearly about 385% because solar energy could be used with a multi-layer, with multi-stages. And also, 1 square meter per hour, you could create 5.78 liters of fresh water. So this is really the high productivity. After that research, also we consider the uses of extreme resisting multi-stage solar desalinations with thermal hollowing convection. Because if original ones, we're using some capillary effect to get the water from the sea and then heat it with the solar. In this case, you create some salt crystal, and then you had the problem. But later we had a new concept for thermal hollowing convection. In this case, we could get continuously flowing and using gravity, this kind of feeding process. In this case, get even salinity needed 20%, we could get 1.8 kilogram per square meter per hour. And then also other papers for solar evaporation with solar replacement toward the real-world applications. We could create the real system that to get fresh water very, very cheap in this case. And also we demonstrate multi-stage MD solar desalination to get 9 liters per square meter per hour. So that's our researches from 0, 1 and 1 to 100. So this research, we have some results. When the results have published, we got a lot of news that this makes every researcher very, very happy because even Chinese government, the central government published the news for our research because the news was from abroad. And then they said, oh, Chinese scientists, they did this work and they published in central government news. And also we got a lot of the basic paper award from SDEWES for Chinese every year. And this is for the 50 years anniversary of SDEWES. And we filled the table. Finally, we had a lot of high impact publications. And also the laboratory is much better. And more publications, and we selected there. And also we expanded the laboratory for the more possibilities. In this case, to attract more fantastic researchers. But meanwhile, we did for atmospheric water commercialization. We innovated a company so-called Atmosphere because it's atmospheric water harvesting. Where is water to get water? So it's sponsored by General Electric Water. So it's they got 51%, our team 49%. In this case, now we have a demonstrator so-called Itawa Park. And so this park, because we had a lot of unit of this kind of prototype, now it's on the way of commercialization. So this is actually the commercialized product. So not only for the room side, but also outdoor units. And meanwhile, we published one paper, commentary for JOR, because we contributed for the review and also for the perspective. And now I think it's time to give a commentary for the approaching thermal boundaries. and how to solve the problem of atmospheric water harvesting. So in this case, I would like to show you a very short video for this Itawa Park, and we try to demonstrate what kind of things there.
Itawa Park, a zero energy park. Here I could show you innovative researches on energy, water, air, and food nexus. So here we see it's a green energy laboratory sponsored by Italian government. So it's we call it Italian Green Energy Laboratory in Shanghai Jiaoteng University, which is equipped with about 60 kilowatt photovoltaics. So now we already connected this to an electrical battery power station. Here you see this is a 256 kilowatt hour battery, and which is used to Itawa Park, a zero energy park. Here I could show you innovative researches on energy, water, air, and food nexus. So here we see it's a green energy laboratory sponsored by Italian government. So it's we call it Italian Green Energy Laboratory in Shanghai Jiaoteng University, which is equipped with about 60 kilowatt photovoltaics. So now we already connected this to an electrical battery power station. Here you see this is a 256 kilowatt hour battery, and which is used to store the energy from the photovoltaic of the green energy laboratory. So in this case, we could gate this green energy laboratory as an off-grid building. Meanwhile, we have another demonstration of off-grid. This is a container box building, and which is shown here. So it's also, the roof is powered with the photovoltaics, but we have also electric battery and also air conditioning. And also here you see the air conditioning inside, but we have also battery stored there for the storage. And we have atmospheric water harvester to produce fresh water from air. So this just shows how a container box could work with only photovoltaic and so electrical battery systems. So this is a second actually off-grid building. We had a third off-grid building actually is here. And because we use this, also photovoltaics with heat pump systems, but also we have the battery inside. So this is actually used for the rooms. So with photovoltaic batteries, and here we have the battery storage, about 10 kilowatt hour, and this is used to support the whole building here, a small building. And also we use air conditioning. I call it as a small temperature difference fan core unit, and which is driven with air source heat pump heating system. So it could be used for winter heating, comfortable heating, and also summer cooling for air conditioning. So meanwhile, this building is equipped with a lot of facilities with clean water for the drinking. And this is a normal clean water drinking, which we have the tap water, and you have get purified water for drinking, and a coffee machine, and so on. But what's important here, I want to demonstrate this is actually off tap water. So it's an atmospheric water harvester. So by this machine, every day we could produce about 15 to 20 liters water actually. So we could use this to put anywhere. If we have the electricity supply, then you could produce water. And here we also show a building outside. So this outside building, and we demonstrate this is actually food nexus, a container box, also powered with photovoltaics. And but inside we have plants just growing inside because we're using artificial lighting for the power to simulate as the sun. So here you could see that what inside it's rotating of the machines and try to get So very good equivalent sunshine for the inside of the container box. So this, we use it for the food processing, but for the food processing, we need water. So we have also this kind of system, so called atmosphere, and this is a container we're using desiccant rotor. That's atmospheric water harvesters. So just using this water and come into the building, and also the building inside, we have another atmospheric water harvesting, just using condensing unit to make just the recovery of moisture water inside. So in this case, this just forms so-called innovative team for energy, water, and air nexus. So we use this as a demonstration as a small park, but also we have 4 independent off-grid buildings. We're using photovoltaics and also batteries. So in this case, we had China, Italy Green Energy Laboratory, and also small container box. And here is another container box for the food nexus. And also here, we're using this as a small conference rooms, also supplied off-grid with photovoltaics. So this is also just a very good demonstration to show how in a campus we could have so off-grid systems. So actually we have 4 off-grid systems that are working together to show zero energy park or zero carbon park. So I hope this demonstration will be fruitful and to have a lot of achievement, and we could get more applications of this kind of systems.
So finally, I think okay, so in this case, our teams is growing up, and there are 4 faculty members, and there are some students, and now some students become faculty members also. So year after year, we are increasing the number, and also we see the changes, and also several young faculty members become the selected national level talents. And also my team, actually is a big team, that's all the faculty members and in my working group. But most of them is not for the nexus. That's normal refrigeration and cryogenics. But for the nexus, only 4 professors involved. And so the group is going up, and so we are very happy with this research group. And so we have a very good basis for the Sino-Italian Green Energy Laboratory, and supported by Italian government. And we had a lot of collaboration also with the Italian universities. So this is actually, finally, we have also mechanical engineering-based laboratory there. There is a much bigger than Green Energy Laboratory. So finally, Mark, so energy, water, air, food nexus, that's a very good area. This research let us understanding from 0 to 1, and also 1 to 100 paradigm. And the most important thing is to inspire young researchers and teamwork, but we need to excel in pioneering innovation from 0 to 1, while try to scale up from 1 to 100. So we are doing our best to try to do this, but I think this is a research story as a professor, how I work with the young faculty members and also the students. Thank you very much, and this is Shanghai. So you are welcome to visit Shanghai during the day and during the night. Thank you very much.
Thank you. Thank you. Sorry. Okay. Thank you, Professor Wang, for the very comprehensive and stimulating overview about these technologies that make these different levels interact one each other. We are, of course, almost in the lunch time. Just time for a quick debate, a couple of questions, because there are a lot of stimulating points. Please, Professor Deutsch.
Thank you for overview of really very exciting research. For me especially, because I had the opportunity to visit your impressive lab. We are going to need a lot of water to green the dry areas. I was wondering, did you estimate the potential of harvesting and multi-stage processes in delivering that? Because with the current system, which is mostly used, reverse osmosis, there is a problem of flexibility. We have lots of very cheap wind and solar electricity in some hours of the day, but solar desalination with reverse osmosis should mostly work flat. We could solve that with batteries, but it would be better if we could have a variable desalination system or harvesting system.
So normally, I think in the seaside, or even some desert area seaside, so we would propose to using condensing unit because it's a more cheap, more high efficient. But there are still a lot of requirement for if the area is far away from river or from the sea. So in this case, atmospheric water harvester using adsorption or liquid adsorption systems. So now we already invented some adsorption unit and also desiccant route system to get about 50 liters per day. And meanwhile, we already had another type for lithium bromide water or lithium chloride water, liquid solution for the absorption water from air. This is more high efficient in combined together with heat pump. Currently also we built a 50 liters per day unit. And so we expect that we could build in the future just upon the demand because technology is available. The most important thing we try to make it that how to get the payback period. If it's less than 5 years, it's easily to be commercialized. If it's more than 10 years, it's no possibility. So in this case, we need consideration to select most advanced materials, but it must be economical, high sorption performance, and also high stability. So in this case, our research laboratory, we had a lot of collaboration with the material people, even for the joint publications. And now we are considering, we taught the material people to not only give high performance material to us, we also need cheaper. Maybe cheaper one, but the performance is lower, but maybe more easily to be commercialized. So in this case, such as our publication in JOR, we asked the material people to consider our requirement because finally for the commercialization, we have several boundaries to overcome. Thank you, Never. Yeah, thank you.
Another quick questions?
Yes. Hello? No, it works. My name is Eberhard Waffenschmidt from Cologne. You showed a slide where you improved the growth and you cooled the soil. Have you ever considered improving the soil with pyrolyzed wooden coal? Because in that case, you would improve the possibility to save water, and at the same time, the coal would reduce carbon from the atmosphere.
Yeah, that's a very important issue. If we use this for the growing plant, if we get water, because I had experience when I visited Middle East countries, Kuwait, for example. So along the airport to the city, they're using spray of water to get green plant. So everywhere is green, but it consumes so bigger water. So if we take water from the moisture, it's a little bit expensive. So normally in this case, we proposed to use hydrogen. So hydrogen actually to make the water to be captured by the hydrogen and in the root of the wood materials or plant. So in this case, water will be freely to be distributed. It's absorbed there, but the plant needed to use the root to take water from there. So in this case, we could save a lot of water in this case. So I think a good engineering, final research work, we need to consider a variety of technologies integrated. So these kind of things like hydrogel should be used for this kind of very specific agriculture. Thank you very much.
Okay,
Thank you for the answer.
I would probably, because of time issues, leave any other question to the lunch time, and so I will greatly thank Professor Ruzhu Wang for this excellent presentation. Thank you.
Yeah, thank you very much. Thank you.
And so please join the lunch now. Thank you.